The general notion involved in this question is as follows. If you have a rectangular slab like this, a transparent slab, and let us say there is a ray of light which is incident on one face of the slab like this. So this is the direction of incidence. Then we are aware that if the slab is of a refractive index which is greater than the surroundings. So for example, typically this slab could be made of glass and the surroundings on both sides could be air, in which case we know that the refractive index of glass with respect to air is typically roughly around 1.5. It could be different, it depends on the type of glass, but this is the rough value. Now of course we are aware that when the ray enters the glass, it's going to bend towards the normal, so it will go something like this, and when it comes out into the air once again, it bends away from the normal, so it goes something like this. Now we have to be aware of one particular result, and I'm sure all of you know that, and the result is that the incident ray, that is this ray, and the final emergent ray, in other words this ray, will be parallel to each other. So if I extend the line denoting the direction of the incident ray, this line is going to be parallel to the line which contains the emergent ray. Now this result is of course valid provided that there is the same medium on both sides of the slab, and secondly the slab must have parallel faces. In other words, this face must be parallel to this face. It must be a rectangular slab for this result to hold. In other words, the only effect of the glass slab on the incident ray is to shift the incident ray, is to shift this particular ray in this direction, and that's called lateral shift. It's called lateral shift, and of course the amount of lateral shift will be given by this particular distance. This is the distance by which the incident ray has shifted laterally before it becomes the emergent ray. So what I can do is to name some points. So for example, the point of incidence I'll call A, and the point of emergence, this point I can call B. Now we want to find the lateral shift, so I must first draw a line segment corresponding to the lateral shift. It would be this line segment. This green line segment, its length is what we want to find. That's the lateral shift. So this angle is of course a right angle, and the foot of this green perpendicular on the red line, I'll give it a name. I'll call it point C. This point is point C, and you now see that I've got a right angle triangle ACB. I want to find AC. Now if I call this angle B, I'll call it theta, then clearly length AC, which is the length which I want to find, that's going to be equal to the hypotenuse's length AB times sine of theta. Now of course theta itself is not given in the problem. The only angles which have been mentioned are the original angle of incidence, which I will call I, and the angle of refraction, which I can call R. I and R, these are the only two variables denoting angles which are mentioned in the question. So I have to express my final answer in terms of I and R. In other words, I have to eliminate theta and write it in terms of either I or R or both. Just to make sure that we know exactly what is I and what is R, I'll just show these angles in this figure, and I can rub them out later if the need arises. So this is the normal which I can draw at point A, and of course this angle is the angle of incidence denoted by I, whereas it is this angle, the angle of refraction, which I denote by R. So that's the meaning of I and R. Now to relate theta with I and R, what I do is to extend the incident ray into the slab like this. It's an extension of the incident ray. The incident ray wants to go in that direction, it doesn't actually go in that direction, and clearly this particular angle, this one, this angle over here, this angle is I minus R. In fact, it is the angle by which the incident ray deviates when it goes into the glass slab. We are talking about this particular angle. This is I minus R. And if you look at it closely, you see that theta is related with I minus R. In fact, it is equal to I minus R, because theta and I minus R form two alternate angles between these two parallel lines, this line and this line. So I'll rewrite this equation as follows. Length AC, which we want to find, is given by length AB times sine of I minus R. Now the problem is, of course, that length AB is not mentioned in the question. The only thickness mentioned in the question, or the only distance or length mentioned in the question, is the thickness of the glass slab, this one, which is given to be T. So somehow there must be a method to express length AB in terms of the thickness of the glass slab, namely T. To do so, I have to form another right angled triangle, and this time the right angled triangle must contain length AB or side AB as one of its sides, and it must contain the thickness of the slab, this thing which I have drawn over here. And then, using normal rules of trigonometry, I'll try to relate the thickness T with the hypotenuse AB of this right angled triangle. Needless to say, this angle is a right angle. So what I can do is to name the foot of this perpendicular. I'll call it D. And now we want to relate AB with length BD, which is nothing but the thickness T. So I want you to look very closely at right angled triangle BDA. Length AB is the hypotenuse. We want to express it in terms of length BD, which is T, and to do so we make use of this angle over here. Now clearly this angle is going to be equal to R itself, this R. Once again, these are two parallel lines, and these two angles which I just talked about will be alternate angles. So this means that this particular angle is nothing but R. And now it's quite easy. What I can do is I can write cos R. So cos R from triangle BDA is of course the adjacent side, which is length BD, and I have to divide that by the hypotenuse, which is length AB. But length BD is nothing but T, the thickness of the slab, divided by length AB. So essentially I have length AB equals T divided by cos R, and it's now very elementary. This T upon cos R I substitute it for length AB in this expression over here, and finally I get my result, namely the lateral deviation of the ray length AC is equal to T divided by cos of R, that's length AB, times sine of I minus R, which is what we wanted to prove